Okay. Well, the first thing to say is this is a maths lecture, and if you come to a maths lecture, you have to expect to do a bit of work. And don't just take my word for it. Here's what a couple of people who wrote about mathematics or mathematicians had to say. You've got to go out to it aggressive and alert like a chess master. Mathematics is not a spectator sport. So remember that. But I won't work you as hard as I work my students, I promise you that. But I will start off with a problem. Now, I want you all to just think a bit about this. We have 4 cards on the table. Each card, you're told, has a number on one side and a letter on the other. And you have to test the hypothesis that a card which has an even number on one side has a vowel on the other. And you're allowed to turn over 2 cards. Which 2 do you turn? And I'll give you 4 possible choices. I'd just like to take a quick vote so we can see what people think. Who thinks that 2 and A is the answer? Nobody, you're ahead of the game. 2 and B? You need more time. You can't have more time, I'm afraid. 2 and B? A few people think that's the answer. Or some other pair? Okay. Who thinks it's impossible to tell with just 2 cards? Okay, so 2 and B seems to be the favourite, but others have some support. We'll come back to that. First of all, the background to this is that I teach mathematics. That's what I do for a living. I think mathematics is important, and I think it's important that we have a new generation of mathematicians coming on, so that's what I'm telling you about. So just to take 2 small examples of why mathematics is important, 2 of my favourite examples. Elliptic functions, their original job was to measure the arc length of an ellipse. Now they are used for, among other things, Andrew Wiles's proof of Fermat's last theorem, and elliptic curve cryptography. When you put your card into an ATM, that is what keeps the information secure as it's transmitted between the ATM and the bank. So rather important. Even more important, perhaps, complex numbers. Complex numbers were introduced to understand the process of solving cubic equations. They turned out to be essential in quantum mechanics, which is the theory of what happens on very small scales. And one of the earliest equations ever in quantum mechanics, which was due to Max Born, P and Q don't commute, but the difference between the product PQ and QP is I, the square root of -1, times some physical constant. And if it weren't for quantum mechanics, we wouldn't have computers. I wouldn't be giving the lecture with this technology. So, again, rather important. We need mathematics, we need mathematicians, but we can never tell which bit of mathematics will be important next. So it's absolutely important that we have people who are ready for whatever comes along, ready for whatever mathematics needs to be done in the future. We have to produce good, able, enthusiastic, passionate mathematicians. How do we do that? Well, there are reasons for doing mathematics. It's a good career, and this has become more widely recognised than it was when I started out. So here's the jobs-rated website. This is the 2009 data, but it hasn't essentially changed. They surveyed 200 professions, and the top profession, the best job to be, is mathematician. Now, I certainly agree with that, but here you are. A mathematician applies mathematical theories and formulas to teach or solve problems in a business, educational, or industrial climate. The overall ranking is 1. Don't worry about the other numbers, but they used some formula and came up with the fact that mathematics is the best job to have. It's a good degree to do. Here, this is from Oxford College at Emory University, from their website. Why major in mathematics? Well, I'll just take you through this quickly, if I can. Here we go. Mathematics is exciting, fascinating, utterly satisfying, rapidly expanding. It has challenge, creativity, clarity. If you like solving puzzles, if you like patterns and hidden structures, logical analysis, deduction, investigating the unknown, connections, if you like to explain and control, then being a math major might be a good choice for you. So, students want to do mathematics. Okay, there's a good job at the end of it, and you can have a lot of fun along the way while you're doing it. But how do we get from this? This is an A-level exam paper, and I didn't use any art or skill choosing this particular question to display. It's just a random question from an A-level paper. You can look at it and make a judgment. Step 1, sketch a graph. Sketch 2. Step 2, sketch another graph on the same diagram. Sketch 3, use your diagram to solve that equation. Step 4, solve a closely related equation. So take 4 small steps and you'll come up with the answer to the question. Here's where we're trying to get to. This is, of course, the title and abstract of Andrew Wiles's famous paper on Fermat's last theorem. Here is Fermat's annotation in the margin of his copy of Diophantus, pointing out that the margin was too small to hold the proof. So, no one gave Wiles a series of bullet points that he had to do to get to the proof of Fermat's last theorem. He had to take rather larger steps and jumps in that. So our basic job is to take people from following in somebody else's footsteps to stepping out on their own. There are various factors that make the problem worse, such as league tables in school. This is not going to be a long rant about league tables, but the point is that at school, the pupils and the teachers are on the same side. It's in both of their interests to get good results, especially to get above the CD borderline, and the examiner is the ogre that has to be slain to get to the next level. At university, it works rather differently. We don't just want the pupils to get at least a C in their exams. We want them to understand what we're talking about and to learn to work independently. And incidentally, we are also the examiners, so we don't want them to slay us at the end of the level. Wouldn't be much fun. Right, so this is the point of what we're trying to do. Now, that looks a bit one-sided, so I should just redress the balance a little by saying there are lots of people in universities who say, you can't call yourself a maths graduate unless you know X or Y or Z, and I don't care what X or Y or Z are. You've probably all heard this kind of statement. We have to keep up standards. People should know certain things. I'm not going to be talking about that at all. I'm just going to be talking about whether we understand what goes on when we do mathematics. Okay, so this is what we did at Queen Mary to address this problem. We developed a new first semester module called Mathematical Structures. The title doesn't matter. I'll come back to why it's called that later, but a first semester module which would only work if it was compulsory for all maths and joint honours students doing mathematics. And indeed, that's what it is. So this module, the idea was it would teach mathematical thinking and understanding, give the students good habits, which they could then transfer to their other modules. So get them onto the right path to follow their maths degree. Right? So this is what we were trying to do. How do you do that? Well, I don't know. But I got the job of doing it. and I was a little reluctant at first. So I would like to thank Thomas Prellberg, who pushed the thing along, and it wouldn't have happened without his support. And in particular, you see, students taking maths or joint degrees have to take this. You have to persuade people in the physics department, the computer science department, the economics department, which is probably more of a challenge, and various other departments, that their students should take this module, right? And it was done. It was done. Right, so it was to be a first semester module, compulsory for these people, designed to introduce them to rigorous mathematical thinking and fundamental objects such as sets, functions, and numbers. So there are the mathematical structures. But you see, these are fairly basic mathematical structures. You can't really do anything without a bit of that. And the idea was, this is not a course about sets, functions, and numbers. It's not just lots of facts about sets, functions, and numbers that you have to learn. The idea is supposed to be something rather different. But you can't, just like you can't do philosophy without something to philosophize about, you can't learn the thinking processes of mathematics unless you have some actual mathematics to think about. So we had to put something in, and we put in the most basic type of mathematics, sets, functions, and numbers. But now, this is why I was a bit reluctant to go along with this. Every module that students take in mathematics at university should have rigorous mathematical thinking, accuracy, and understanding in it. It's not really mathematics if it doesn't. So we have to somehow not create a ghetto so that the students go into that course, know that they're supposed to think logically, and then they go off to do geometry or calculus or something else and say, that's it, we just have to learn stuff now and cram facts into our brains. We absolutely didn't want that. So there was a fine line to be trodden there. So anyway, this is what we set out to do. So here is the structure as it actually came out. It turned into 10 chapters in the end, roughly speaking, a chapter a week in the lecture. So an introduction, where I said some of the things that I've already said to you, but also gave them a proof, which I will inflict on you later on, sets, infinity, functions and relations, various number systems, in the end proofs, and finally, my favourite part of the course, constructing and debugging proofs. How do you spot a mistake in a proof? It might be a proof of something which is obviously nonsense, or it might be a proof of something which is plausibly correct, but the proof itself might have a bug in it. How do you spot that? So that was the last part of the course. Anyway, so this is what we ended up doing. The idea, as I said, there's not too much content in there. If you have a week to talk about natural numbers, you can probably get some of the basic things across without too much straining. So, but to back this up, along with the basic material that was in the lectures, there was also supplementary material, which may have been historical or philosophical. It may have pushed the development on a bit further and contained proofs of things that weren't proved in the lectures or other stuff like that. There was a range of things that went into the supplementary material, including more examples, something that students always ask for. More examples, more examples. Well, at least I could point them to the supplementary material and say, read that, you'll find some more examples. And as well, a lot of things went into this module which are not just mathematics in the strict sense. So, for example, study skills. There are a lot of things that people don't tell you about taking exams and revising for them and things like that. So I did, in each section of the notes, have a little part on study skills. So if you're learning from notes, if you see a word that you don't understand, what do? You go away and look up the definition. We all understand that very well, but beginning students don't necessarily understand that. What to do in the exam room? Well, lots of people don't get the best out of themselves in an exam. I try to give some advice to help them to do that. And everything was supposed to be open and transparent. Everybody could see what I was doing. And one of the students asked me about this in the first lecture, and I said, this is an experiment, you're the guinea pigs. Nobody objected too violently to that. And it was what happened, as well as what was actually presented in the lectures, is all documented. You can go away and read about it if you really want to. And part of the thing that made the course work was lots of interesting examples and exercises and problems. And I'll talk about the role of those later on. But it was very important to have problems which were not just standard problems about the material in the course, standard questions about sets and functions and all that kind of stuff. Questions that required the students to be, if I can put it this way, light on their feet, not bogged down in the particular topic that we'd been talking about that week. Because I think that's also an important part of the training. And I'd like to mention Chris Budd, who provided me with a lot of these examples, which I made good use of. Thanks, Chris. Okay, and then so there were many things in the notes, but some of the things in the notes were the kind of details. How do you read that formula? Well, I didn't have a formula like that in the notes, but you can't avoid Greek letters. When I was a student, one of the books I had to read was in German, which I didn't speak very well at the time, but the symbols were fractal capitals, and I still to this day am not quite sure. One of those is a G and one's an S, but I am not sure which is which, and therefore I didn't feel I could inflict any of that kind of stuff on my students. So we kept mostly to Roman letters, but as I say, you can't escape Greek. You have to know pi apart from anything else. So one of the things that the students got early on in the course was the Greek alphabet, capital and lowercase, how to pronounce it, and a suggestion that they should go away and practice writing these letters until they could do them without too much thought. As you all know, there's quite a difficulty about psi and zeta, because they look roughly the same but have different number of wiggles, and so students tend to put an extra wiggle in psi just so that it won't be confused with zeta. Blackboard bold is another new set of things that they have to learn about. But now, how do you write things like that in your notes? Well, I've printed N and Z here. These, of course, are names for standard number systems, but some of the others are not. It's not quite so clear how to quickly write them into your notes. You have to be able to do that without stopping to think, because if you have to stop and think how you write this character down, it will break your concentration. So you have to practice doing that. So I actually wrote them out in handwriting myself and scanned them in and put them in the lecture notes as a suggestion of how you might do it. You have to know the difference between A over B and A divides B, which I'm afraid to say some of my students still don't. I've been marking the exams this week. They're not just different functions. That's a function, but that is a relation, and they're completely different logical objects. Tutorials. Now, this was the other thing that contributed enormously to the success of the module, and this is something else that I have to thank Thomas Prellberg for. We went back to small group tutorials, which is something that we'd abandoned years ago as being just impractical. Only in this module did we have small group tutorials. And they were put on for two reasons. The other reason is that students now choose their modules online, and the student's advisor gets a message to say the student has chosen their modules, please approve them. If you don't approve them, you have to not approve them, and it goes back to the student. And this all becomes terribly inefficient. But students are reluctant to come along and see their advisor unless they have to. And we were finding ourselves in the position of having to write references for people who'd never been inside of our offices for the entire length of their degree course. And so it was a way of getting around that. What we would do is the student's tutor would be their advisor. They would have to go and get to know their advisor because that's where they went for tutorials. It seemed to work. I'll say more about that later as well. Of course, the slight problem with that was the economics students who didn't have advisors in the maths department, so we had to hire a couple of PhD students to give them their tutorials. But for all the rest, the tutor was their advisor. So I'll say something about how the tutorials worked out later. And part of this goes together with these interesting questions, not just about the material in the course. I wanted the students to want to go along to the tutorial, either to explain their ideas on a problem or to get somebody else's ideas. And tutors were encouraged to get their students to go up to the board and say what they'd done on this problem and things like that. So we tried as much as possible to get the students interacting in the first semester at university. Okay, so we have to have bureaucratic things like learning outcomes, and what are they called now? I can't remember. Whatever they're called now, these things that used to be aims and objectives, they keep changing. But anyway, the main thing that I managed to get in was this phrase here, which to me summarizes exactly what I was trying to do in this module. It was to be precise but not pedantic. Mathematicians are very good on pedantry. We all know that. But first-year students may well be put off by pedantry. What is a function? Is it a set of ordered pairs? Well, it wasn't in my course. I'll tell you what a function was in a minute. I gave a precise definition of a function, which I think is actually in some ways superior to the ordered pairs definition, but it was not pedantic. So anyway, this is what I was aiming for. So this is what it said on the web page. You don't have to read 1 and 2 because they're just the boring stuff that you have to have in. 3, to get you involved in the excitement of doing mathematics. That's what the module was really about. I wanted the students to enjoy this and to be excited about what they were doing. And all of these various different things that I was putting in were supposed to somehow get that to work. And if that worked, then everything else would be absolutely fine. So this course was about the excitement of doing mathematics. Well, of course, I'm not the first person to do this, it would hardly be said. Other people have done it before, and I made a point of not reading up what everybody else had done because I wanted to do it myself, try my own ideas out. Now I should probably go back and read some of those things and pick up some good ideas that I missed first time around, but if I find time to do that, I might. But I would like to mention Kevin Houston, who has this lovely book, How to Think Like a Mathematician. How many of you know this book? Not many. He has a web page which has a short PDF document on it called 10 Ways to Think Like a Mathematician. So you start reading it. Number 1, question everything. Now that's the most important rule for doing mathematics. Question everything. You can prove it for yourself, and if you can't, then you've got no reason for believing it. You don't believe it just because I tell you it's true. You figure it out for yourself. So question everything. And we're in good company here because this is essentially what the Royal Society have for their motto, but it's absolutely crucial for mathematicians. And the second one is write in sentences. Writing a piece of mathematics is not like writing a code or something like that. It's meant to be read. And if you do your exam and you write out the answer to a question and I can't understand what you're saying, you're not going to get many marks for it. So write in complete sentences. Don't just write strings of formulae connected with equals or double implication signs or something like that, as a lot of students tend to do. Tell me exactly what you're doing. So that was the aim of 2. So you can go away if you like and read the other 8 of Kevin Houston's 10 Ways to Think Like a Mathematician, but I read the first 2 and I was absolutely sure that he was getting it right, so I just stopped there. Well, I had so many other things to do at the time. Anyway, I would like to say a little bit about starting off doing mathematics. So here's the mathematics department at the University of Queensland, where I was an undergraduate. And I must say, when I look at that picture, I do still get a little bit nervous because the flowering of the jacarandas meant exam time. So it's changed a little bit since I was there, but basically it's flat at the front, but at the back it's on the side of a hill. And so if you go in the front door, which is over there somewhere, you can either go down to the basement or up to the upper floors. Mathematics is a bit like that. You come in at the front door knowing various things that you already know, like what numbers are and measurement and a few things like that that you just pick up, as everybody has to. So numbers and space and all this kind of stuff. Well, there's stuff in the basement. There's foundations down there in the basement, logic and set theory and those kind of things. Or upstairs there are analysis and group theory and many other subjects like that. But you come in at the front door with what you come in with what you know when you arrive at university. And what I was trying to do was take that and work from there. Not say, oh, you've got to forget all that, here's a whole lot of new stuff that you have to learn now. Just to start from where the students were and go on from there. Right, so you'll see some of the consequences of that philosophy. I'm going to go now in a little bit of detail through the actual material in the course to show you how these ideas worked out in practice. So, sets and functions. Well, what is a set? You can't really say. If a set is a collection of things, what's a collection? What if a collection is a class? What's a class? And you end up going round in circles. So you cannot, in an elementary way, define what a set is. So we just have to say, well, we know roughly what a set is. You take some things and you bundle them together. And of course you have to be a bit careful, and we talked about that and Russell's paradox and so on, but we didn't worry too much about that. You can recognize a set when you see one, basically. So I did not attempt to define sets. But here are functions. So, as I said, a function was not a set of ordered pairs. It's a black box. You put an element of the domain into the black box. Something comes out at the other side because the black box applies this function to it. Now, the name of the function is written on the box, and the domain and the codomain are part of the specification. If you read the manual for this black box, it will say, these are the things that you're allowed to put in. Don't put anything else in or the machine will jam. And everything that comes out is guaranteed to be one of these, right? So the domain and codomain are part of the specification of the function. And that's everything now. We've now got all the information about a function right there, because everybody nowadays can understand, here's a black box, it does something, but I've got a manual, I can look it up and find out what I'm allowed to put in and what I can expect to get out. So here's just a little example that was in the notes. So you see I'm not being pedantic here, that's not really the name of a function. But let's pretend it is. So when I put 3 in, 12 comes out. And if you read the handbook for this function, it'll probably tell you the domain and the codomain of the set of real numbers. Natural numbers. Well, that's something that everybody really does know when they come to university, indeed long before. So I'm not going to teach you over again what natural numbers are. You know what natural numbers are. But we do have to look at them in ways that you may not have looked at before you went to university. The key property of the natural numbers is that you can, in principle, start at 1 and count up to any natural number. You may not be able to do it in practice because the number might be so big that it would take you longer than your lifetime to do it. But in principle, you can start at 1 and count up to any number. That is the absolutely crucial property. So this is a rhyme that my children used to say when they were in primary school. James probably remembers this. 1, 2, Mr. Few, 99, 100. That's the quick way to count to 100. But that's the mathematician's way of counting to 100. 1 dot, 1 comma, 2 comma, dot, 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 comma, 99, comma, 100. That's exactly the same. That is the symbols for that little rhyme. So that's the one thing to remember about the natural numbers. Integers and rational numbers we had to do next. And I didn't actually say much about those. An integer is plus or minus a natural number or 0, and a rational number is the quotient of two integers. But of course there are some difficulties, and I didn't entirely ignore the difficulties. I didn't say anything about this in the lectures, but you see, you can go from the natural numbers to the integers. And the most straightforward way of doing it is what I just told you, that an integer is plus or minus a natural number. So it's a natural number with either a plus sign or a minus sign in front, or it's the number 0. And there it is. But now if you want to add two integers, what's the rule for adding two integers, each of which is plus something or minus something or 0? If you work it out, you'll find that there are 13 separate cases that have to be considered. And that is exactly the kind of thing that I was trying to avoid. So, mathematicians have a better way of doing it. Basically, the way we do it is to say integers can all be obtained by subtraction of natural numbers, so we can represent them by pairs of natural numbers. And now, of course, many pairs of natural numbers represent the same integer, so we have another problem to worry about. But what is really going on here, that pair AB is really an equation, isn't it? It's B plus X equals A. So think of it as an equation rather than an ordered pair. It will be more transparent to you. So an integer is, well, this equation represents an integer, but many other equations represent the same integer, because the equation 6 plus x equals 5 represents the same integer as 3 plus x equals 2, or 100 plus x equals 99. So we have bags full of equations. We never look inside the bags unless we really have to. The important thing is we have names for these bags, and the names are written on the front in big friendly letters, or digits. So minus 1, here are all the equations that we want to have minus 1 as the solution, all the equations we want to have 0 as the solution, and 1, and so on. But as I say, this is, in general, this is the way mathematicians cope with sets. So when we talk about infinity, there's a lot of discussion about how do you think about infinity? How can a finite human mind comprehend infinity? Well, the answer is, of course, we have an infinite set. We put all its elements into a bag and write the name of the set on the front, and then we don't have to worry too much about what's in the bag. And it's the same thing going on here. So this is something which, if you've done a mathematics degree, you may have seen the construction of integers as equivalence classes of ordered pairs of natural numbers, but to me this is what they really are. They're bags of equations. And using the bags of equations approach, we can define addition and multiplication without any case-by-case at all. Real numbers. And once again, real numbers are something that you have at least some intuitive idea of when you go to university. Probably as points along the line, or as infinite decimals or something like that. So I just simply said a real number is an infinite decimal. And we don't have this representation problem very badly. There is a small issue because 0.99999 going on forever is the same as 1.000 going on forever. Well, is it? One of the things I got the students to do was to I set them a question which said, you're at a party, somebody comes up to you and says, you're a mathematician. Well, mathematicians say that 0.999 and so on is equal to 1.000 and so on. I don't believe that. That can't be true. What do you say to that person? How can you possibly try to convince them that that is the case? So I got the students to think about that. I'm not going to talk about that now, but I simply defined the real numbers to be infinite decimals. And then you can prove things like they're uncountable. Every positive real number has a square root. You can even prove the principle of the supremum if you want to. There are some difficulties, though, and I didn't mention these to the students. I just skated over them, I must admit. If I have to add this number, 0. Never mind what the digits are, each digit here adds to 9 with the corresponding digit there, as far as I've gone. Now, is that number greater than, equal to, or less than 1? You don't know, and you won't know, possibly, until you have the complete infinite decimal expansions for both of them. So that's a bit of a tall order. So there is a problem with defining real numbers to be infinite decimals, but let's not worry too much about that. It's a good way to think about them, and that's really what I was after. Okay, now we get to something which was perhaps even more important, reasoning and logic. And I like what Julian Jaynes says about reasoning and logic here. I'll leave it up for a little while. You can read it if you like. What he's saying, in a sense, is that reasoning is what we do in everyday life. Logic is what we wheel on when our reasoning lets us down or doesn't work quite properly, and we have to be a little bit more formal about things. So he would say the everyday world is very little concerned with objective truth. So reasoning happens unconsciously, and it's only when it has to be brought into our consciousness that we have to deliberately apply logic. I think that's roughly how it goes, but the point is, when you're doing mathematics, you're likely to be confronted rather more often than in your everyday life, sitting on the sofa watching the television, with questions about, what really is going on there? What's the logic behind that argument? So you are going to have to trot this logic out. If you do, and do it several times, then, as with practicing any skill, it will become independent. Your reasoning will become better. So implication is a little bit of a stumbling block for new mathematicians. A implies B. If I said that in, or words equivalent to that, in a non-mathematical context, you would think I was saying there is some causal connection between A and B. They're not totally separate events. There's some relationship between them. But mathematics doesn't ask for there to be a relationship between them. The statement A implies B is simply a logical proposition which is either true or false. It's true unless it happens that A is true and B is false. In all other cases it's true, but in that one case it is false. And people say, well, why do you do that? So we have a little example. If it's fine tomorrow, I'll take you to the zoo. Well, I haven't lied to you unless it's fine tomorrow and I don't take you to the zoo. In any other situation, my statement is true. Well, that exactly agrees with the rule for implication that I gave you up there. So that's why we take that as the rule for implication. And, well, there are other reasons, but it at least makes sense. If you refer it back to this example, you see why we've chosen that particular definition. So back to this problem. Here's the problem. Here are our cards. Each card has a letter on one side and a number on the other. You have to test the hypothesis that a card with an even number on one side has a vowel on the other. So we've just talked about implication. You now have the tool in your hand which will solve this problem for you. So what is the answer? 2 and B, right? Because the only way that this hypothesis would be false is if there was an even number on one side and a consonant on the other. So we have to check the cards that have an even number or a consonant, and that's 2 and B. Either of those could refute the hypothesis. Nothing else we can do will refute the hypothesis. So the answer to the question is 2 and B. So most of you got it right. Well done. But on the subject of this, probably quite a lot of you know Ben Goldacre's book, Bad Science. It's a lovely book, full of good things, but his attitude to mathematics is a little bit scary. He always comes to a bit of mathematics and said, this is really difficult stuff, it makes everybody's head hurt. And if you get people like Ben Goldacre saying things like that, then of course people will think, oh, I can't do maths, it's too hard for me. So I don't like what he does with that. But then he comes to this very problem. Now, to him, this is not mathematics. This is only a logical puzzle, and it doesn't make anybody's head hurt. Well, it's logic, it's mathematics. They're so closely related that you can't say where one stops and the other starts. So anyway, there's the solution to that problem. And now, closely related to this is one of the most important proof techniques in mathematics, proof by contradiction. And this is what G.H. Hardy had to say about proof by contradiction, which he called reductio ad absurdum. It's one of a mathematician's famous weapons. It is a far finer gambit than any chess gambit. A chess player may offer the sacrifice of a pawn or even a piece, but a mathematician offers the game. The mathematician says, I'm trying to prove A, so I will suppose that A is false. And if that leads me to a nonsensical situation, then I'm sure that my supposition was wrong and that A is, after all, true. So we can suppose that A is false, but we must be able to get from there to a contradiction. So I will go quickly through Euclid's proof, because this is what I did right at the start of the course. I went through Euclid's proof, which I'll now do, and then I'll tell you what I said next. So here's the proof that there are infinitely many prime numbers, and I hope at least some of you have seen this proof before. So we're going to prove it by contradiction. So what do? We suppose that the theorem is false, that there are only finitely many prime numbers, right? If there are finitely many, then we can call them P1, P2, P3 up to Pn, right? It's only a finite number of them. I can, in principle, multiply them all together. Now, I mightn't be able to do that in practice because these primes might be so large that this product is far larger than will fit into any computer, and perhaps larger than the number of particles in the universe, and so on and so on. This might be a very large number, but in principle I can do that. And then I add 1. And I say, let's look at that number. Well, it's obviously bigger than any of P1 up to Pn, because we multiplied them all together and added 1. So it can't be the same as any one of those numbers, and therefore it must have a prime factor, which is must be in this set, because these are all the primes there are. But that's impossible, because when I take this number, capital N, and divide it by any of these, I always get a remainder of 1, because I multiplied them all together and added 1. So none of these numbers divides, and we have a contradiction. So I gave the students that proof, and I said to them, the proof is meant to be convincing. Are you convinced by that proof? And if you're not convinced by that proof, your job is to tell me why not, and let's see if we can sort it out. And I'm very pleased to say that a lot of students took me up on that and raised various objections. There is one serious objection to this proof. Can anyone point out what it is? Yes? Very good. You've heard this before. How do we know that each number must have a prime divisor? Yes. How do we know that? I'll come back to that. It's a very good question. I got a lot of good questions, but that was the one that forced us to go and do a bit more work. So anyway, here we are. The students had to be convinced by the proof, and if it wasn't convincing, I hadn't done my job. And the weak spot in the proof is, why does n have a prime divisor at all? Well, you can prove that every number bigger than 1 has a prime divisor, and the tool for that is induction, which is the most important property of the natural numbers. So, here's induction. Now, I claim that if you understand this picture, you understand induction. You don't have to worry about what they tell you in the textbooks. We've got a long line of dominoes, I don't care how long, potentially infinite, as long as you like, and I guarantee you that when any domino falls, it will knock the next domino over. What happens when I push over the first domino? Well, it's not hard to see what happens. They will fall over, right? If you understand that, you understand induction. That is induction. So here's what you read in the textbook. P of n is some statement about the natural numbers. Suppose that P of 1 is true, and that P of n implies P of n plus 1 for any natural number n. Then P of n is true for all natural numbers n. And the reason is, we let P of n be this. So if we go back to the previous picture and say, let P of n be the statement that domino n falls over. The second bullet point here says that if domino n falls over, it knocks over domino n plus 1. That's the promise I gave you. And the first bullet point says, I push over the first domino. Then they all fall over, so P of n holds for all natural numbers n. But look at that statement there. Look at that. Which is more understandable? Which is more intelligible? I think this one is. I think if you get that, then you understand induction, and it doesn't matter if you can't reproduce that in an examination. You understand induction. So that's my point there. And in a sense, that argument is at the heart of the whole course. Everything I did was on the philosophy of saying that you can see that all the dominoes fall over, you understand induction, that's all you need. So, as I say, that's to be understood, but you might have to know this so that you can trot it out in an exam, possibly. Okay, so, but why is it true? Why is induction true? Well, we said that the crucial property of the natural numbers is I can start at 1 and I can count up to any number whatsoever. So I start at 1, property P holds there. Then property P holds for 2, then it holds for 3, and then I can miss a few, it holds for 99, it holds for 100, right? So it holds for all n. So that's induction. But you see, if you go back to this way of stating induction, students get into all kinds of trouble over that. Assume P of n and prove P of n plus 1. But you're assuming P of n, and that's what we're trying to prove. Aren't you going around in circles? And then there are some who misremember it and say, oh, I have to prove P of 1, P of n, and P of n plus 1, and then I can conclude that P of n is true for all n. If you've ever marked exam papers, I'm sure you've seen that. So people write that because they haven't got in their head that picture. That's my claim. Anyway, false proofs. So this was the last part of the course, false proofs. As that Julian Jaynes quote said, sometimes you have to wheel out the apparatus of logic, do it consciously, and find out what's wrong with the proof. So here's an example which I gave. All horses have the same colour. Hope some of you at least have seen that. Here are some horses. Do they all have the same colour? Maybe, hard to tell. So, proof by induction. Let P of n be the statement, in any set of n horses, all the horses in that set have the same colour. We're going to prove that by induction. So we have to prove P of 1. If you have a set with only one horse in it, then clearly all the horses in that set have the same colour. No problem. Now the inductive step. We assume P of n is true and prove P of n plus 1. So take a set of n plus 1 horses. Here they are, h1, h2, hn plus 1. I'm assuming they're not moving around, so they're in stalls or something like that. And that's important for the argument. So you look at h1 up to hn, that's a set of n horses. They all have the same colour, right? That's our induction assumption, P of n. Look at the horses from h2 to hn plus 1. That's a set of n plus 1 horses. A set of n horses, sorry. They all have the same colour by the induction hypothesis. So all the horses have the same colour. And our induction proof is complete. I'm not going to tell you what's wrong with that. You can go away and think about that. That's your homework. Okay, so I said that small group tutorials were an important part of the course. So how did the tutors react? Well, I think it's fair to say that there was a little bit of unease at the start, particularly since this was sprung on the tutors at rather short notice, and they didn't know what was going to be expected of them. This is a pretty big ask, actually. But the start of the semester, two of my colleagues had a bet. One claimed that the students would stop turning up at tutorials by halfway through. I'm happy to say that he lost the bet. The students were still coming along and even emailing apologies by the end of the semester, which I think is absolutely remarkable for something like this. And I think there were two reasons why they kept coming along. One, because the tutors were giving them something of value, and two, because the problems were interesting to them and fun. They were enjoying doing the problems. So these things can work, that's the point. So here's a comment from one tutor. Good engagement with the group. Some people don't know how to write mathematics down. That's the big problem. That's the problem which this course hasn't really solved. The students can understand it, they can get up at the board and talk about it, but if you ask them to write down a formal proof, they maybe can't do that, because with the excitement of tutorials, this boring stuff about writing out your solutions and handing them in tends to get sidelined a bit. And so we haven't quite solved everything, so there's that. But anyway, so you see, generally nice problems to talk around in exercises 1 and 2. I enjoyed the tutorials. So if the tutors are saying that, that's a good sign. I'll come to what the students said in a moment. Right now, actually. So, sorry, I have to look over my shoulder because I would normally have a screen here that would have the thing on it, but for technical reasons, that's not possible. Anyway, so here are some of the comments from the student questionnaires. Different view of maths than I had previously encountered. Not just taking small steps one after the other, actually turning on your brain and thinking. Lectures interesting, some history, philosophical thoughts. Tutorials are very helpful. Small classes enable a lot of learning to be done. Intervals at the appropriate times for questions. So I give a proof and I stop and say, are you convinced? And if you're not convinced, tell me why not. And I particularly like the last one. It won't work unless you have that. All of this would just not work but for that. So I think that's essential. Well, of course, not all student comments are positive, but there were many positive comments about the small group tutorials that I haven't given here. On the negative side, well, it wasn't really asking for negative questions. It was asking how we could do better. And if you've ever lectured, you will know that there are students who say, more examples. Okay, so I'll tell you another little story here. I went to a conference in Michigan once. I got off the plane at Detroit and got the airport limousine to the conference. There were two people sitting in the back who were obviously mathematicians, so I went and introduced myself and we sat in the back and talked together. They were Christian Krattenthaler and Sergei Fomin. And Sergei Fomin was at MIT at the time, and he said, I like your combinatorics book very much, but I can't use it at MIT because it's got theorems and proofs in it, and the students just want examples, examples, and more examples. And for MIT, that's a little bit depressing, isn't it? But anyway, that's a well-known phenomenon. Students asked for more tutorials. Indeed, some of them said, we want tutorials in all our modules. And of course that's not practicable, and we simply had to say so. So I said, in reply to that, I said, tutorials are for you to use, but they are not a security blanket, and you're not going to get them in the future, so make the best use of them now. Students asked for notes to be put online in advance of the lectures. I don't do that. The notes go up afterwards. They have to come to the lecture, engage with the material, and then the notes give them a check on whether they've understood it or not. So now I'd just like to slightly embarrass Vicky perhaps by quoting her email to me at the end of the module. This is just to show that I think, at least in one case, possibly others, it was a success. So this is what she said. You made the transition from A-level to university much easier for me. You taught me to look at mathematics in a different way, and I feel I am now able to approach this course in the way I should after learning mathematical structures. So that was exactly what we had in mind when we set up the module. Give the students the tools to think about mathematics and to attack mathematics. These skills will then transfer into all the mathematics modules that they take at university. And here, what about this? Approaching the midterms, mathematical structures was the one I was most worried about, as it required a different approach compared to the others. But after reading through my notes, I realized that I actually knew most of the material. That's because there isn't a lot of stuff to learn. It's to be understood. And once you've understood it, you're not going to lose that understanding in the run-up to the exam, are you? So that is a pretty good sign that it worked, I think. And anyway, so that was the email. So I think it could be said that the course was a success. It's going on again next year. We'll see if we can get it even better next year. So that's the end. Thank you for your attention.